Note Packet 4 revolves around the idea of complex numbers. We're going over complex numbers now because we've been doing a lot of stuff with radicals lately, and complex numbers are used a lot when it comes to radicals. For instance, we did talk before about how the square root of 25 is equal to the positive and negative version of 5. For the reason being that 5 times 5 is 25 and negative 5 times negative 5 is 25. But what if somebody gave you something like this, and then you were asking yourself, what can I multiply by itself to get negative 25? And there's really no number you can multiply by itself to get a negative outcome. So what we would say with negative 25 under the radical symbol is that it has a non-real answer. Now this is because also the index here is a positive number. If I had a cubed root, then you would have a whole different thing going on, but we're going to be talking mostly about square roots. Complex numbers come into play because they allow us to work even further with something like the square root of negative 25, because we're now introducing this concept that is I, and I is not part of the real number system. It's actually part of the imaginary number system, and I is equal to the square root of negative 1. This allows us to be able to simplify radicals that are not located in the real number system, and take them and make them more simple. So I can break the square root of negative 25 into the square root of 25 times the square root of negative 1. Now I have that plus or minus 5, and instead of writing negative 1, I can now write I. A lot of times you'll see situations where your complex number has a portion of it that is real and a portion of it that is complex. In other words, we're going to actually say this is imaginary. It's part of the imaginary number system. If there was a number alone paired up with I, we would say this is purely imaginary. Just like if I saw a number out here by itself, I would say this is purely real. And then you can have them grouped together like this. We wouldn't be able to simplify them any further because they're not like terms. Let's focus a little bit on I. I've already told you that I alone is equal to the square root of negative 1. Sometimes you'll see I raised to a power. For instance, I squared, which is the square root of negative 1 times the square root of negative 1, which is negative 1. We have I cubed, which essentially is negative I. I to the 4th power is the square root of negative 1 times itself 4 times, which is negative 1 times negative 1, which is positive 1. I to the 5th power is negative 1, the square root of negative 1 times itself 5 times. If you go ahead and you do that, you're going to end up right here. I to the 6th power, once you work it out, is going to give you negative 1. I to the 7th power is going to give you negative I, and I to the 8th power is going to give you 1. Maybe you're noticing that there is a pattern here, and that the pattern is that there is a cycle. Every 4th root, you will reset to the beginning again. It's kind of interesting, because if you're in a situation where you want to simplify an I that's raised to some crazy power, let's say I to the 27th power, what you need to do is figure out how many times 4 goes into 27. In this case, 4 goes into 27 6 times with a remainder of 3. 3 is really the important thing, that remainder, because it's telling us that I to the 27th actually is the same thing as I cubed, which is negative I. So if we're operating with complex numbers, there's a few different things you're going to want to know. For instance, you can add and subtract complex numbers. You do it very much like you would with dealing with like terms. So I can only combine the real numbers together. 8 combined with a positive 2 is 10. Negative 3 combined with a positive 5 is 2. And you just have to remember that if there's an I and you're adding, the I stays the way that it is. I can't simplify this any further. The next one, we can't really do much unless we distribute that negative symbol, and when we do, we end up with something that looks like that. I can combine 9 and negative 12, and I can combine negative 6 and negative 2, and there is my complex solution. The last one here, again, because it's adding in the middle, 8 plus 7i minus 12 plus 11i. I can combine the real numbers and I can combine the imaginary numbers, and I have a complex result. Multiplying complex numbers isn't too bad either, as long as you're making sure that you're critically looking at what's going on when you're multiplying. Before I start multiplying, the two that I have here, I'm going to convert these so that they are written with I terms. So this first one is 5 times the square root of 2 times the square root of negative 1, which if I were to simplify that further would be 5 radical 2i. And then the second one, 4 times the square root of 4 times the square root of 2 times the square root of negative 1. If I were to take the square root of 4, that is 2. Keep going here. Now if I look at this, what I'm looking at is 5 times the square root of 2 times I times 8 times the square root of 2 times I. 5 times 8 is 40. The square root of 2 times the square root of 2 is 2. And I times I is I squared. If I were to look at my I table, I squared is equal to negative 1. So simplified, you're going to have negative 80. Okay, so let's take a look at our next example. It's a little bit different from the first example because these complex numbers come in the form of two terms. And I have to deal with this just like I would deal with multiplying binomials. I would have to use the FOIL method or double distribution. If I was multiplying 8 times 2, that's 16. 8 times negative 3i is negative 24i. 5i times 2 is 10i. And then 5i times negative 3i is negative 15i squared. Just a couple things to remember. First thing is I squared is equal to negative 1. Second thing is I have two terms that are like terms in here that I can combine. (16 minus 14i plus 15). If I combine my two terms that are like terms, my end result will be 31 minus 14i. This example here dealt with in the same way. I'm going to FOIL or do the double distribution. I end up with negative 6 times 2, negative 6 times negative 3i, 2i times 2, and 2i times negative 3i. Combine the like terms in the middle. Change I squared to negative 1. And combine the last two like terms. Let's go to the next page. On the next page, we're looking at complex numbers, which we're going to have to deal with division and the idea of a complex conjugate. So a conjugate basically is something that you can create based on a binomial by writing another binomial that has the opposite symbol. What? I'll show you what I mean. We're going to go ahead and rationalize the denominator. Now, rationalizing the denominator should not sound like something you've never heard of before. We're basically making the denominator have no imaginary parts. And I can multiply this by some kind of fraction that is equivalent to 1 and also the conjugate of 2 minus I. Just like with radicals, I would multiply the top, multiply the top and the bottom by 2 plus I. Oh my goodness. And again, we're going to have to do this in the way where we are foiling on top and foiling on bottom, and as you would expect on bottom, the two middle terms are going to cancel out, and that's the nature of conjugates. You're going to end up with 2 times 2 and negative I times I, which is negative I squared. On top, 16 plus 8I plus 2I plus I squared. We know that I squared is equal to negative 1. On top, 16 plus 10I minus 1. On bottom, 4 minus negative 1. On top, 15 plus 10I after I combine like terms. And on bottom, we have 4 minus minus 1, which is 5. Believe it or not, on the top, you can do a little bit of factoring. You can factor out a 5. And inside the parentheses would be 3 plus 2I. And on bottom, I have a 5, so I would be able to cancel out those 5s. And the end result would be 3 plus 2I, which is the equivalent of what we started off with. It just has a rational denominator. Let's look at the next one. We're going to multiply this by the conjugate of the denominator, so the top and the bottom should be 3 minus 2I. I like to put parentheses to remind myself I have to FOIL or double distribute. On top, 3 times 3, 3 times negative 2I, 3 times negative 2I, negative 2I times negative 2I, positive 4I squared. On bottom, 3 times 3 is 9, negative 6I, positive 6I, negative 4I squared. Let's keep going. On top, 9 minus 12I plus 4 times negative 1. On bottom, 9. Two middle terms cancel out. Minus 4. Instead of the I squared, I'm going to put negative 1 on the bottom. 9 minus 12I minus 4. Just simplifying. Double negative is positive, so we're going to say plus 4 on bottom. The last part of this is pretty much simplifying. 9 combined with negative 4 is 5. On bottom, 9 combined with positive 4 is 13. This is our solution. Okay, we have a third example. Sorry that this is so wackadoodle. The third example has 5 plus 2I over 7 plus 4I. The conjugate that we're going to be multiplying everything by is 7 minus 4I. On top, 35 minus 20I plus 14I minus 8I squared. On the bottom, after working everything out, I'm going to have 49 minus 16I squared. Combining like terms and replacing I squared with negative 1 on top, I should have negative 6I minus 8 times negative 1. On bottom, 49 minus 16 times negative 1. 35 plus 8 minus 6I. 49 plus 16. So I have 43 minus 6I on top, and on bottom, 49 plus 16 is 65. If I were to look at using the square root property to solve quadratics, sometimes the end result of it is going to be that you're going to need to know all of the different properties of radicals, including how to use I to enable you to be able to complete a problem. For instance, here I have 4x squared plus 100 equals 0. I could subtract 100 from both sides. I could divide both sides by 4. And then I could take the square root of both sides. Remember, when I do that, I need to do the Plinus symbol because this is a positive index. And the answer that I'm going to get here after I simplify the square root of negative 25 is plus or minus 5i. Where did 5i come from? Please recall in the past, if you have a negative, you can break it up into two different radicals and replace the square root of negative 1 with I. It's a different kind. This is, we could call this the square root property to solve quadratics, and it works well if you don't have an x term in the middle. The next one, let's go back there. I'm going to subtract 48 from both sides. So 3x squared equals negative 48. Divide both sides by 3. X squared is negative 16. Take the square root of both sides, Plinus. This will be 4i. Two answers, positive and negative 4i. The square root of 16 is 4. The square root of negative 1 is I. On this page, we have a bunch of different examples. I think that the best way to look at this is if I have you do each of these individually, and you're just going to have to do a series of pausing and playing to check and see if you have the right answer. So now would be a time to pause. I'm going to do number 1. I'm going to unpause, show you the answer, and so on and so forth. So pause and do number 1 now. For number 1, I noticed that 144 is actually a perfect square number. I can break up 144 and negative 1. The square root of 12, or the square root of 144 is 12. Negative 1 can become I, and that is simplified. Go ahead and pause for number 2. For 2, I'm going to simplify my radical by breaking it down into 25 and negative 1. And the 25 is going to become 5. The negative 1, radical negative 1 is I. You have a complex answer. Go ahead and pause for number 3. For number 3, we can break down the square root of negative 49 by pulling out 49 and negative 1. 49 becomes 7. The square root of negative 1 becomes I. Number 4, I'm going to break down this radical by multiplying 4 times 5 times negative 1. Notice that the square root of 4 is 2. 5 is not a perfect square, and negative 1, the square root of negative 1 is going to become I. If I do number 6, they want you to simplify I to the power of 35. So I need to know how many cycles of 4 we've gone through and what the remainder is. I know that 4 goes into 35 8 times with a remainder of 3. 3 is the important thing here because that means that this is equal to I to the third power. And I to the third power is negative square root of negative 1. You would want to keep going with that and make it negative I. Number 7. I need to figure out how many times 4 goes into 62. 4 goes into 6 once. Goes into 22 5 times. So our remainder is going to be 2. So this means that I to the 62nd power is equal to I to the second power, which is negative 1. I missed one. Nice. I missed number 5. Let's go back to number 5. If I'm going to go ahead and break down 12, I'm going to pull out a 4, a 3, and a -1. Basically, I'm trying to pull out anything squared if I can. So the square root of 4 is 2. My square root of 3 is going to stay the way that it is, and my square root of -1 becomes I. Now I guess we can jump down to number 9. There's no 8. Oh, lies. There's 8. Oh, look at this. You know that 16 is a multiple of 4. So if you were to go ahead and divide 16 by 4, your answer is going to be 4 with a remainder of 0. There's two ways that you can look at this. I to the 16 is the same thing as I raised to the power of 0, and anything raised to the power of 0 is 1. Or you can just treat 16 as you would treat all of the 4th powers on the I chart. And so I to the 4th power is 1. And so either way that you look at this, you'll know that you'll end up with the correct answer. Anything that is a multiple of 4 when we are looking at powers of I is going to give you a result of 1. For number 9, looking at my I chart, I know that I cubed is equal to -I. I also know that I to the 9th, 4 goes into 9 twice with a remainder of 1. So that's the same thing as saying 7I, I to the 1st power. And I can't convert the -I, but I can change this entire term to -4I. I can rewrite that because I'm actually multiplying them, and then you can acknowledge that these are actually like terms that can be combined one last time. So your answer to this would be 3I. For number 10, you're going to use your laws of exponents. And remember, the laws of exponents state that you can do one of two things. You can either write this out twice and multiply it, or you can put both of the factors inside to the 2nd power. Either way, you're going to end up with the same answer. This is going to be 9I to the 10th. Remember that 4 goes into 10 twice with a remainder of 2. So this is 9I squared. On my I chart, I squared is equal to -1. So I have a purely real result, which is -9. Oh, I almost tried to skip one again. I knew it. Okay. So really, this is just based on your ability to break i's down. Remember that I to the 16th is the same thing as I to the 4th, which is 1. I to the 10th, 4 goes into 10 twice with a remainder of 2. So this is I squared, which is -1. I to the 8th, 8 is a power of 4, so that's 1. And then we have I to the 14th. 4 goes into 14 3 times with a remainder of 2. So this is an I squared, which is -1. So you have 1, -1, +1, -1. The result for this is going to be 0. Number 12. 12 is a power of 4, so this is 1. Power of 4, multiple of 4. I squared is equal to -1. I to the 8th is a multiple of 4, so this is 2 times 1. What I end up having here are 3 real terms. My answer for this is going to be -6. In this case, we are adding complex numbers. I don't really need to do anything to get rid of these parentheses because I have a positive, so I can combine like terms. 5 combined with -2 is 3. 7i combined with 6i is 13i. For number 14, I have to distribute my -2 and then combine my real numbers and then combine my imaginary numbers for 6 minus I. Here we are with 15, distributing my -2. I have 3 minus 2, square root of -18 minus 2 minus 3, the square root of -8. And these need to be broken down so I can see if I can go any further with it. So when I'm breaking down the square root of -18, I'm going to make that radical 9, radical 2, radical -1, which you know is I. And when I'm breaking down -8, I'm going to say 4 times 2 times -1, which is essentially I. 3 minus 2. This is a perfect square. This is not. This is I. This is a perfect square. This is not. This is I. So I have 3 minus 6 radical 2I minus 2 minus 6 radical 2I. I have two terms here that are like terms, so I can combine the 3 and the -2 to get 1, and then I have minus 12 radical 2I. Craziness. Number 16, this is one of those situations where you're going to have to do the double distribution or FOIL. 5 times 3, 5 times 4I, -2I times 3, -2I times 4I. I squared is equal to -1. So I have 15. I'm going to combine these two like terms. And then my last thing is combining our last two like terms for a final answer of 23 plus 14I. 17, double distribution. 9 times 9, 81. 9 times -3I. 3I times 9. 3I times -3I. Get rid of these middle terms. 81 minus 9 times -1. I changed my I squared. And this gives me 81 plus 9, which is 90. Those happen to have been conjugates. Number 18, perfect squares. I have to write this out twice and then double distribute. Oops, let's go back. 4 times 4, 4 times -3I, -3 times 3I times 4, and -3I times -3I. 16 minus 24I plus 9 times -1. And 16 combined with -9 is 7 minus 24I. Here is the end result. Everything looks very microscopic. Here we are at the next page. Lots and lots of practice is probably the best way to go about this. The next few of these, the next two of them are going to be multiplying, just like FOIL. And then we have 21 and 22 that we're going to look at. I'm going to start with number 19 if you want to pause and do it on your own. 5 times 2 is 10. 5 times negative radical -9 is -5 radical -9. Negative radical 16. Radical -16 times 2 is 2 radical -16. And then I have radical -16 times negative radical -9. Oh my goodness, that's kind of a tongue twister. So that's going to be negative, and then inside of this I'm going to have -16 times -9. Okay, so I'm going to have to break some stuff down. -9 is going to become the square root of 9 and the square root of -1. 16, the negative 16 is going to become the square root of 16, the square root of negative 1. When I put negative 16 times negative 9 in the calculator, I get positive 144. 10 minus 5 times 3 times I plus 2 times 4 times I minus 12. Simplifying and seeing what's left, I have two sets of terms that are like terms. 10 combined with negative 12 is negative 2. Negative 15i combined with a positive 8i is negative 7i. Number 20, I see that they're conjugates of each other, which means the two middle terms are going to cancel out. 9 times 9 is 81. Negative I radical 2 times positive I radical 2 is negative I squared times 2. So 81 minus, and I have 2 times negative 1. I just kind of put this over there. 81 minus negative 2 is 83. We have a division problem. 10 minus 5i divided by 5. I know that if I factored out a 2, I would have, oops, what did I say, 2? That's not the GCF. I want to factor out the GCF. It's 5. I'm going to put in here 2 minus I, which will allow me to cancel my 5s and have a final answer, 2 minus I. One minus 2i divided by 3i. We need to rationalize the denominator. I also know, because of my i's, that my denominator could be rationalized if it ended up being either I squared or I to the fourth power, because I squared comes out to be negative I, and I to the fourth power comes out to be 1. So if I did put this, I'm going to go ahead, if I multiplied this by a fraction that has I cubed on top and I cubed on bottom, the result on bottom would be 3i to the fourth power. This essentially is equal to 1, so on the bottom is 3. And then on top, I have I cubed times 1 minus 2i, which would give me I cubed minus 2i to the fourth. Again, I to the fourth is 1. And just to make sure that I'm thinking of everything, I cubed is negative I. So I can simplify that a little bit if I want to and have negative I minus 2 all over 3. I can rationalize the denominator of number 23 by multiplying this by a fraction made up of the conjugate of the denominator, which is 1 minus I. On the bottom, since these are conjugates, I know that my end result is going to be 1 minus I squared, which is 1 minus minus 1, which is 2. And then on top, I'm going to have the FOIL method to find out that 2 times 1, 2 times negative I, negative 3 times I, and negative 3i times negative I is positive 3i squared. But I squared is equal to negative 1, so I have 2. I'm going to join those middle ones together, and then I have minus 3 on the end. Let's bring this down. 2 combined with negative 3 is negative 1, and I still have on the bottom 2. (24) conjugate. It's my favorite word right now. The conjugate of 3 minus I is 3 plus I. On the bottom, I'm going to end up with 3 minus I squared. On top, I'm going to have 15 plus 5i plus 6i plus 2i squared. 15 plus 11i plus 2 times negative 1 all over 3 minus I squared. I have not even yet simplify the I squared, but I'll do that in a second. If I combine 15 with negative 2, I get 13, and then I have the 11i still up there. Remember that this is equal to negative 1, and 3 minus negative 1 is 4. Here is your end result. I'm going to solve my equation. It's my quadratic by using the square root property and what I know about complex numbers. If I have x squared equal to negative 27 and I take the square root of both of these, I would definitely need to do this thing first where I have a Plinus sign. I'm also going to break down negative 27 to 9, 3, and 1 so that I can pull out a 3. I have a radical 3 and I have an I. There's two solutions, BTW, the positive and negative version of 3 radical 3i. Same deal. X equals Plinus 9i. It's getting to the point now where whenever you see a negative under the radical, you just know that you can replace that negative symbol with an I that is out from under the radical. Add 9 to both sides. I have 4x squared equals negative 32. Divide both sides by 4. X squared is equal to negative 8. Take the square root of both sides. Plinus. We have 2 radical 2i. 2 answers. Okay, let's do this. Maybe we can change how this looks by completing the square. If I can get something squared on one side equal to something else, then I can use the square root property to solve it. For instance, what if I were to start by subtracting 7 from both sides? So I have x squared minus 2x equals negative 3. And then I wanted to complete the square, so I have to take half of b, half of negative 2 is negative 1, and then square it. So I would be adding 1, and I can't add 1 to one side, I gotta add it to both sides there. Okay, that's great. And so now I can write this as half of b, x minus 1 squared, I made that a perfect square trinomial, equal to negative 2. So I just completed the square to change this. I didn't put it in vertex form, but what I'm doing is I'm putting myself in a position where I can do one of these puppies. So now I have x minus 1 equals Plinus, the square root of negative 2. Also, x minus 1 is equal to Plinus, square root of 2i. And if I add 1 to both sides, I have solved for x. Remember, I'm going to put the 1 in front, and then I'm going to say plus or minus the square root of 2i. You leave the answer like this, and that is a-okay. There's two solutions there. There they are. Let's try more of those. Solve quadratic equations using the square root property. I'm going to take 2 away from both sides. I am going to leave 12x, some space, negative 2 over here. Half of 12 is 6, and 6 squared is 36. If I add it to one side, I got to add it to the other, and it allows me to rewrite this as a perfect square trinomial, and this is equal to 34. If I were to go ahead and take the square root of both sides, I would have x plus 6 equals Plinus 34, the square root of 34. And if I subtract 6, x is equal to negative 6 plus or minus the square root of 34. Yeah, you can leave it like that. Even if there's no i's involved, that's okay. Doesn't mean anything bad. Let's go to D. I'm hoping that on these you are pausing here and there and trying them on your own. I am going to start by subtracting 11 from both sides. And then half of negative 12 is negative 6, and negative 6 squared is positive 36. So I have x minus 6 squared equals 25 Plinus. I have x minus 6 equals positive and negative 5. You add 6. Now you have two solutions. You have positive 5 plus 6, and you have negative 5 plus 6. One of those solutions is 11, and one of those solutions is 1. All right, I'm going to move my 2x to the left. X squared minus 2x, big space, negative 6. Half of negative 2 is negative 1. Negative 1 squared is positive 1. This allows us to rewrite the left-hand side as the perfect squares. Negative 6 plus 1 is negative 5. Take the square root, Plinus. And then I'm going to have x minus 1 equals Plinus the square root of 5i. Add 1 to both sides. My answer will be x equals 1 Plinus radical 5i. Two solutions for that one. For e, add 59 to both sides. Leave, oops, it's not x. Let's go back there. Leave a little bit of space and cut 6 in half and square it. So half of 6 is 3. 3 squared is 9. Make sure I add it to both sides. And then I have v plus 3 squared equals 68. I have v plus 3 equals Plinus 68. And it behooves me to probably break down 68, but let me just do that in a second. I'm going to subtract 3 from both sides. So I have v equals negative 3 Plinus the square root of 68. I know that 68 can be broken down and simplified a little bit further, so I'm just going to do that really quickly on the side here. 1 times 68, 2 times 34, 3 times, nope, 4 times, yep, 4 times 1, 17. There's a perfect square 4. So if I take the square root of 68 and I make it 4 times 17, then I can simplify that to 2 radical 17. So Plinus 2 radical 17. Beautiful. Let's take a look here. Okay, so I'm going to add 15 to both sides. So I have 2x squared plus 8x equals, and then I have 15 over here. I'm going to factor out my 2. And I'm going to leave space. So right now, everything is equivalent. If I cut 4 in half and make it 2, and then I multiply 2 by itself, this becomes plus 4. I cannot put a plus 4 over here because this is not just a straight plus 4. It's actually, if you think about it, inside these parentheses. So over here, I actually have to plus 8 to compensate for the 2 on the outside of the parentheses. Now I have 2 times x plus 2 squared equals 23. I can divide both sides by 2. That gives me x plus 2 squared equals 23 divided by 2. I'm going to leave this as an ugly fraction. Square root x plus 2 equals Plinus the square root of 23 over 2. And then the last thing is to subtract 2. So x is equal to negative 2 Plinus the square root of 23 over 2. Can you leave it ugly? Sure. Leave it ugly. It's all good. Last one, huh? Let's factor out, well, let's get rid of 36. Minus 36. 4n squared plus 4n, big space. Let's factor out our 4. N squared plus n. Half of 1 is half, and half squared is 1/4. So this is going to look like this. 4n plus 1/2 squared equals negative 36. Oh, wait a minute. If I added 4 here, I need to compensate for it on the other side. 4 times 1/4 is 1. So I have to add 1 over here. I have to add 1 over here. So now I have not actually negative 36, but I have negative 35 that I'm going to divide by 4. Okay. So I have n plus 1/2 squared equals 35 over 4. If I do the square root of both of these, I have n plus 1/2 equals Plinus can do this 35 over square root of 4 for good reason. N plus 1/2 equals minus radical 35 over 2. Subtract 1/2 from both sides to have your final answer. Fun times in the neighborhood. Fun times in the neighborhood. After doing this, I kind of realized too, where we ended up with this is not exactly simplified all the way, because those simplification rules that we went over before stated that we can't have an answer that has a radical in the denominator. So I actually have to rewrite this as something with a rational denominator. Remember that we can break it down. All we would have to do to rationalize the denominator is to multiply the top and the bottom by radical 2. That would give me 2 on the bottom and radical 46 on top. Can 46 be simplified? I do think so. 46, 23, 2 times 23, 4. Maybe not. 1 times 46, 2 times 23, 6 times 7. No, you can't. I guess that's it. So the answer for this one was, if it's proper, -2 plus or minus radical 46 over 2. We didn't do that one all the way because I almost didn't see that. Okay, this is a long video. Hopefully you survived it. It's a lot of stuff. I shall see you next class.